Hello, welcome, and thank you for choosing to learn with Materialise. My name is Dries Vandecruys. I'm the Engineering Services Manager in our manufacturing division here at Materialise, and I have worked in 3D printing for 13 years. Today, I will give you a quick introduction to design for additive manufacturing focusing on polymers. In this session, I'll cover the design process, the importance of design for EM, plus some helpful examples taken from real-life cases. Let's get started. What determines the performance of a part? In order to investigate this, I have compared a traditional garden chair with an additive manufactured topology optimized car seat. The three parameters which determine the performance of a part is design, the shape of the application, the material where this application is being made out of, and the manufacturing process. If you look at these percentages, if you look at these parameters in a conventional manufactured garden seat, we see that actually the design determines 45% of the performance of the part, equally important as the material where this garden chair is being made out of. The manufacturing process has a very small influence on the performance of the part. If we compare this with additive manufacturing, we see that these percentages are different. The design plays a very big role in the performance of the part. The material and the process only, both of them have a 20% influence on the performance of the part. Why is this, and why is this different than in additive manufacturing than in conventional technologies? Is because in additive manufacturing you have a lot of freedom of design, you have a lot of opportunities to improve your design, to overcome limitations on the material or on the process side. So in general, you can use your design freedom to adjust your design for printability and optimize your part for the printing process. I have a few examples to explain how you could do this. So a first explanation, you have probably seen this framework before, where all these AM technologies are being mapped out. With most of these manufacturing technologies, support material is necessary. Support material is necessary for the printing process to support the part and keep it in place during the printing process. The orientation of a part on a 3D printer determines the amount and the layout of the necessary support. It is always a compromise between different parameters: the building time, the total cost, the building risk, the post-processing efforts after the printing process, the preparation time, and the surface quality of your part. Always dependent on the orientation, it is a compromise between these 6 parameters. Of course, what you can do is that you can overcome these process limitations by designing smart. For example, what you see here on the screen is an example of a toy car which is being printed in FDM, so in one of the manufacturing processes where support is necessary. Printing such a toy car is of course very fun, but it is only fun if the wheels of the toy car rotate and if you can drive your car and it's not just a static object. In order to do so, you can imagine that whenever you have an axis in your design, that in FDM printing, this axis would be filled with support material, and that would limit the function of the wheels of this car. What we see in this redesign and in this beautiful design is actually that the axes, as you can see here in this cross section of matrix, is that these axes are designed in such a way that they can be support free. So what this designer has done is that he has used the freedom of design and his cleverness to overcome the support necessity of this manufacturing technology. So he has designed a part which actually, by using his design freedom cleverly, he has eliminated the need for support material and therefore created a design which can be reduced support-free around the axis and therefore having a fully functional toy car in the FDM printing process. So this is a very good example of how you can adjust your existing design to overcome difficulties of the manufacturing process. Also, what you can do is that you can look at your design to improve your part and to overcome limitations on the material side. An example for this is an application which we have developed together with this car manufacturer. And this is an alignment fixture to apply logo stickers on the trunk of a car, on the backside of the car. What you see here, of course, is not the 3D printed design, but was the original design, which is a combined design where metal beams are being welded together and milled pads are there to apply the logo on the backside of the trunk of the car. This feature was relatively heavy and quite complex to source or to get to the exact location. We looked at this application and we redesigned an additive manufacturing version of this alignment fixture. This additive manufacturing version, we focused a lot on having a lighter weight, and we thought, okay, how can we do this? How can we make a lighter weight and still have the necessary stiffness for this application? We decided to work together, so we decided to make a hybrid design, combining additive manufacturing with conventional manufactured components. So in this case, what you see here is a combination between carbon rods, traditionally manufactured carbon rods, and 3D printed connection beams in order to make up the skeleton of this application. Of course, this sounds very well. This is a beautiful idea, of course, but there are some difficulties with this idea, some difficulties in creating this idea. One of the first difficulties is that it is impossible to directly glue carbon and polyamide 12. So that's the material where these knots are being made out of. There is no glue available in the world which can glue directly on polyamide 12 and on carbon itself. So we were a little bit stuck there. What did we do? We used our clever design and we thought, okay, what can we do in order with our design freedom to overcome this material restriction of not being able to find a perfect material match between the 3D printed material and the traditional manufactured material. So we came up with a clever shape, what you see here. And what we have done is that we have selected a glue which attaches to the carbon rod and created a 3D printed cavity, which then can be filled with the filler material or the glue in this case, in order to create a mechanical interlocking between both the components. So the 3D printed part is there as a container for the glue which is being inserted and ensures the mechanical interlocking between the two components. So the carbon rod on one side and the polyamide 12 component on the other side. So that's a very good explanation of a very good example, which lead to a very accurate design, which had weight reduction, cost reduction, and achieved all the requirements. So that's a very good example of how we can use our design freedom to overcome limitations or the limited amount of materials. Of course, in order to do so, you really need to design for our additive manufacturing technologies, and that's where our following presentations and the following videos that's the topic of the following presentations. Thank you for joining this session, and don't hesitate to reach out to our expert and the contact address that you will find at the end of this feed. Thank you very much for your attention.
So there you have it, a first look at designing for EM using polymers. If you'd like to learn more about this topic, keep an eye out for the dedicated sessions coming up soon. In those videos, we'll share, amongst other topics, some expert advice on what to consider when designing for additive manufacturing in metal. In the meantime, you can also explore more content like this via the links below. If you have any questions about our courses, our services, or anything else related to 3D printing, you can get in touch with our team at the address you see on the screen. Thank you again for learning with Materialise. We'll see you next time.